Hello, Siobhan again. This time we're going to have a look at how we might approach sample L. So sample L, when we do the bromine water test, no reaction occurs and the orange colour remains. So this means that we probably don't have any carbon-carbon multiple bonds, a double bond or a triple bond. So we're probably not dealing with an alkene or alkyne functional group. When we do the oxidation test with sample L, the solution goes from orange to green, which means a reaction has occurred and oxidation has taken place. This means our molecule could have an alcohol or carbonyl functional group, and in particular primary or secondary alcohol, because tertiary alcohols don't undergo oxidation using this reagent, or an aldehyde in terms of the carbonyl group, not a ketone. And then when we do the carboxylic acid test, we don't see any bubbles, so we don't have a carboxylic acid group. The next thing I look at is always the IR, remembering that from about 1500 downwards is the fingerprint region, and we don't tend to worry about that region. So then I truck up from 1500. Here I'm not seeing any significant signals until I hit about 2900, 3000, which we know is where we see those CH IR signals, so CH vibrations. And then if I continue moving downwards, we see this very significant signal, which is really easy to identify. Having a look at where it sits, it's sitting at about 3,300, which puts it in the range of being an OH signal. And we know due to its broadness and also how intense it is that it's probably an OH signal. Amines tend to be a little bit smaller, sitting a little bit higher up. The next thing I like to look at is the mass spectrum. And remember, you go all the way to the end of the spectrum, and sometimes it's not always clear. So we're not stopping here, we're stopping here. This is our molecular iron peak, which will give us the mass of our molecular iron. And this can be plus or minus a hydrogen, depending on the type of mass spectrometry experiment we've done. So our mass of our molecular iron is 74. Now at this stage, you can always have a quick squiz at your carbon NMR, your carbon-13 NMR, because that will tell you how many carbons you have in your molecule. So I had a quick look before and we have 4 carbons, which means, and I know we have an alcohol, so we're going to put in 1 oxygen, and that leaves us with 10 hydrogen to make up this mass of 74. Now this 74 sitting all the way down here doesn't have a second mass peak, so we're not looking at any halogens, we're not looking at any bromines or chlorines because we don't have that second peak. Confirming that we do have 4 carbons, we have a look at the carbon NMR, so 1, 2, 3, 4. Usually at this stage I don't worry about picking up too much from the carbon NMR, but this signal here does stand out at around, let's say 63, and that could be indicative of a carbon that's attached to our alcoholic oxygen. Sitting at between 50 to 90 is where you see that signal. So this could be due to our carbon attached to an oxygen. And if you like, you should write that on your note paper. The rest of it, I don't worry about too much for now. Now we get to the exciting part, which is our proton NMR. And that's where we can start building up our molecule. We know that our molecule has 4 carbons. So I always like to put in my carbon chain first, if I can. Now we don't know where our alcohol is going to sit, and that's fine. We're going to work it out as we go along. What I always do is start from the 0 to 1 end of the NMR spectrum because you're looking for a signal that looks like this. This is a dead giveaway for a certain part of your molecule and is the easiest place to start. We have a signal that integrates for 3 protons and it's split as a triplet. And a lot of compounds, when they are quite simple, will have this signal. It is a CH3 group sitting next to a CH2 group. Now, you may not be able to identify the signal for the CH2 group right away, but you can definitely identify the signal for the CH3 group. We then move on and see that we have a signal for 2 protons, so a CH2 group, another 2 protons, so another CH2 group, and another 2 protons for another CH2 group. This will tell you where the alcohol in your molecule sits, because if we had an alcohol sitting on either of these two carbons, we would only have one proton, and we don't have any signal that integrates for one proton, which means our alcohol will be sitting on a terminal carbon. And this will mean that whatever our other signals are, they're going to integrate for 2 protons each. So this is probably our final molecule, but I always do a double check. Here we have a CH3 group that's next to 2 protons, so this should be a triplet, which we can see here. It should be upfield because it's not next to any electronegative elements, so it's not being de-shielded. Then we have these two CH2 groups, which could be any one of these signals. We can knock off this signal here because it's attached to, the carbon's attached to the electronegative oxygen. These 2 protons are going to be de-shielded and shifted downfield, so it's probably this signal here, which makes sense because these 2 protons are next to 2 other protons, so they will have a triplet signal which integrates for 2. And this hydrogen here we always see as a nice small broad peak because this hydrogen is popping on and off in a hydrogen deuterium exchange in our NMR solvent. And this hydrogen here is actually acidic. So if you think about HCl, it gets lost. Or if you think about hydronium ions going to water, it's popping off the oxygen like that and leaving an oxygen with a negative charge. So then that just leaves these 2 signals here. Because these 2 protons are attached to the carbon that's attached to the oxygen, they're probably going to be shifted more downfield. So that's probably this signal here. But we can double check because they are next to 4 protons. So we would expect this signal to be a quintet, so having 5 signals or being split into 5 signals. So 1, 2, 3, 4, 5 confirms that this proton environment here corresponds to this signal here, which means that these protons here next to 1, 2, 3, 4, 5 other protons should present as a sextet signal. 1, 2, 3, 4, 5, 6. We can confirm that this signal here corresponds to this proton environment here. And if you like to finish off everything nicely, we can mark in which signal corresponds to which proton environment. Now we've worked out that we had a terminal alcohol, so this would be a primary alcohol, but we could have had a secondary alcohol. Imagine if the alcohol had sat on one of these 2 groups. How could we have identified that? Here we have one example of butan-2-ol, and in fact you can only get butan-2-ol in this case because if we put the alcohol here it would again be butan-2-ol. But let's think about how this NMR spectrum would change if we had our alcohol on the second carbon. So if we had our alcohol on the second carbon and we draw in all our hydrogens, we would still see this signal here. And now this proton here would only integrate for 1. And it is next to 1, 2, 3, 4, 5 protons, so we would expect it to be a sextet. Then we would still have this signal here. That would remain mostly unchanged. Then we would expect around this region here a CH2 group, so integrating for 2 protons, that's next to 1, 2, 3, 4, so we would expect to see a quintet. And then we would expect to see a signal that integrates for 3 protons, 1, 2, 3, sitting next to, we would expect to see a doublet. So that's how you can double check that it really was butane 1-ol, not butane 2-ol, by thinking about how the NMR spectrum might change. Again, I hope you found that explanation useful.